This is a final presentation for CSE573 Winter 2021 on Q-learning for speed. In this problem, I apply reinforcement learning to find a good way to accelerate to a top speed in a human-powered vehicle before becoming fully fatigued. The motivation is a race that happens called the World Humans Powered Speed Challenge. It happens in Nevada around September every year. You can see that the current record achieved is in 2016 of 89.59 miles an hour by a team called Aerovelo. Also, everybody wants to go fast. So a little more detail on the problem definitions. The goal is to go as fast as possible, only under human power. On the right here, I show a couple pictures of the Aerovelo team. They've got their racing shell here and the outer profile on the top, and then the insides on the bottom of what these vehicles kind of look like. The speed challenge happens on State Route 305 in Nevada. They've got 5 miles to accelerate, and then your speed is calculated over a 200-meter distance. And I would like to apply Q-learning to accelerate to these speeds. So the approach on Q-learning, I've got on the left here, I've got some definitions, and on the right, I've got a kind of example starting state space here. So on the left, the environment is comprised of the rider who has some weight and they have some cycling capability. The vehicle has some weight, a frontal area, and a drag coefficient. And the environment also has some air density, just some physical components of the environment that are governing the speed that's achievable. The action space is just power, so the rider can input power through force on the pedals at a cadence. The state space is comprised of only velocity and fatigue. So velocity is just the speed of the vehicle, and fatigue is the current buildup of fatigue for the rider. On the right, I show an example of, every simulation is going to start at 0 miles an hour with 0% fatigue, and at a time step, after a time step of 1 second, putting in 100 watts or 200 watts, you'll achieve some new velocity and have accumulated some fatigue, and the space, the Q states build from there. The action space is discretized. Power input is continuous, but I've discretized it in order to create a reasonable size state space. Fatigue, I've created a sort of model of fatigue that only accumulates, and it's measured from 0 to 100% fatigue. When I say it only accumulates, I mean it cannot diminish. It does not reduce over time. And it's governed by this formula here of fatigue is equal to T over T max. T being the duration of time that you're inputting some power, and T max being the total amount of time that power is possible for this rider. So I've put a little dot here that shows that a rider can sustain, 400 watts on the y-axis for a total of 5 minutes before being fully fatigued. So if you input 400 watts for 1 minute, you will be 20% fatigued. Velocity is governed by this power equation I've reproduced in the top left, and I've put in some definitions and value ranges for the variables that exist in this equation. But suffice to say that velocity and acceleration can be calculated given a known power input and all these environmental variables. The vehicle that I am putting through the simulations is a symmetric NACA airfoil. It's rotated about itself just to make a volume, and I've done some CFD simulations to determine the drag coefficient and frontal area of a vehicle that might be able to fit a person to go through this race. Okay, the rider. Again, I'm showing a fatigue kind of curve here on the right, and on the left I'm showing that the rider contributes to the mass and really none of these other factors, environmental factors. But I show a couple curves here, an 80th percentile and a 95th percentile rider, just to show that the more capable the rider, the more power they can put in for a given duration. The reward is is velocity over fatigue plus 1. I'm adding 1 to fatigue because it can be 0, and I don't want to divide by 0. And this just incentivizes velocity and penalizes fatigue. So why Q-learning? Well, the acceleration to the top speed in this problem is really important. And the problem is really too large to solve through search in a reasonable time. Though the size does depend on the fatigue discretization, the speed discretization, the power discretization, and how long of a time step you take. I wrote a little formula here just to calculate how many state action pairs are possible, which is, the number of fatigue discretizations times speed times power. And I've reproduced the Q-learning time step update equation here. And this is what I implement in my Q-learning. So for my setup, I've got these hyperparameters, and I take a time step of half a second. I take random actions 25% of the time and have some discount. I also, an important factor is that I limit actions to within plus or minus 50 watts of the last action taken. I do this just to keep things realistic. A driver is really unlikely to kind of wildly oscillate between hundreds of watts every half second. So I'm just trying to keep things realistic for the driver of the vehicle. So what happens when I train up an agent, a Q-learning agent here to try these different accelerations? So what you're looking at now is a semi-log plot of power over log time. And you can see that in general, these simulations kind of trended towards low power inputs and then increasing power input as time went on. A couple strange simulations here in the orange and the brown, but eventually they did the similar actions of increasing the power eventually to accumulate fatigue and accelerate. Another semi-log plot here of velocity on top of time. You can see that the velocity is just increasing up to some maximum, and these top 10 runs actually hit very, very close top speeds. Fatigue, similar. The fatigue starts at 0 and accumulates as the agent takes actions to increase or decrease power input. But as the power input increases, fatigue increases faster and faster, and you need more and more power to speed up. So the trend is to higher power inputs and higher fatigue accumulation. So what happens when I finally put the agent to the test? The agent was able to reach 68.8 miles an hour before becoming fully fatigued. When I tried this combination of vehicle and rider simulation, I was able to manually achieve about 67 miles an hour. So the Q-learning beat at least some manual efforts to make this to solve this acceleration problem. And I've reproduced those same plots here for the final agent. Sort of most interestingly is probably the top right plot that shows how the agent chooses power over time to approach this maximum speed. Okay, so was this a success? Well, manually I tried to improve upon the Q-learn best sequence of actions to maximize velocity, and I couldn't. So I call that a bit of a success. And the algorithm was actually quite successful with very few iterations. I ran only 250 training runs to get to the agent that I showed the results of here. And this agent's capable of building up a power input over time to accelerate to a maximum speed for any number of vehicles or rider capabilities or different environments. For instance, different air densities and vehicle drag coefficients. So that could be very helpful in iterating with different designs or trying to get different riders to achieve their maximum speed in a fixed vehicle. So I showed just a simple diagram here to show that the vehicle, rider, environmental conditions can be put into this Q-learning algorithm. It can run and spit out a sort of optimal acceleration profile over time to allow a rider to achieve their top speed. Thanks for listening to my presentation, and I hope it was interesting. I'll make the slides available.